So, welcome back. As we discussed in the introduction, our module 1 will cover topics of chemical thermodynamics, okay, and here we will talk about we will basically review some parts of classical thermodynamics. We will go into energy conservation, and using energy conservation we will show how adiabatic flame temperature can be obtained. And the material of this talk or of this lecture is mainly taken from combustion physics by C.K. Law, combustion by Glassman, and also combustion and an introduction to thermodynamics and an introduction to thermostatics by H.B. Callan. And this is a very classic text in thermodynamics which you might be aware of. So, why do we need to understand chemical thermodynamics and combustion? Now, chemical thermodynamics deals with the description of equilibrium states of reacting multi-component systems. Now, as you would recognize, a combustion is essentially deals with reacting multi-component systems. Of course, there is reactions, and because of reaction you have heat release, and of course, it is multi-component because you have fuel, you have oxidizer, and you have different kinds of products, right, and also might be intermediates. So, it is a study. So, to understand that what are the equilibrium states of combustion, we need to know chemical thermodynamics. Now, in a practical combustion process or in any process as such, most processes as such, the reactions, the chemical reactions, especially combustion reactions, cannot reach completion. Okay? Rather, the products of combustion will acquire the state of chemical equilibrium. Okay. So, to understand the composition and the temperature of the combustion products, okay, which is governed by chemical equilibrium, we need to understand chemical thermodynamics. Now, then you want to ask, okay, if does in the most practical combustors is chemical equilibrium reached? Now, the target is to ensure that chemical equilibrium is reached. Okay. Now, we need to design combustors such that fuel and air have sufficient residence time to mix and react and attain thermodynamic equilibrium. Okay. But depending on the flow, on the speed of the flow, thermodynamic equilibrium may or may not be reached. We will come to that. For example, in a gas turbine combustor, your residence times are large. Flow residence times. Flow residence times you can simply obtain by the length of the combustor divided by the velocity of the fuel air mixture of the airflow speed, that is mean airflow speed that is inside the combustor. So, this you can define as the residence time. Now, in a gas turbine combustor this is large. For example, in a scramjet combustor this can be very small, because in a scramjet combustor your U is very large, right. So, in a scramjet combustor you may not have thermodynamic equilibrium, in a gas turbine combustor you may or may not have thermodynamic equilibrium, okay, but the target is to ensure that it is reached. Now, when you do a first cut design, an engineering design, you do not need to go into the different things like how a flame looks like inside a combustor, how the flame structure looks like, how does the flow look like. When the first, of course, those are needed for optimizing the combustor or optimizing the engine, but for the first cut analysis you need to know what is the heat and the power output that you can obtain from the combustor, okay, and that can be estimated by assuming thermodynamic equilibrium of the combustion products. So, that is why in thermodynamic equilibrium and chemical equilibrium is a very important tool that we must know for combustion engineering. Okay. So, the basics of combustion, the basics of the combustion engineering are thus covered here. So, now practical reactants, what should undergo combustion, and the product of what should be in chemical equilibrium? Fuels. So, what are the question is what are the fuels? Gaseous fuels can be hydrogen, carbon monoxide, methane, ethane, propane, butane. If it is greater than 5, if the number of carbons is greater than 5, typically they are liquid. And in the previous introduction introductory lecture, we have seen the importance of liquid fuels because of their very high energy densities. Okay. And then we also have alcohols, and for other purposes, for power generation purpose, we might have coal, woods, etc., metals, which is not of importance in this course. So, fuels, liquid fuels and gaseous fuels are of primary importance in this course, which are mainly hydrocarbons. Now, oxidizer. Now, the great thing about, the most important thing about air breathing combustion, air breathing engines as such, is that here of course you are carrying the fuel in the fuel tank, but the oxidizer you are taking from the air, from the atmosphere. So, this has a great benefit that you are not carrying the oxidizer with you, which reduces the payload of the which allows you to carry some other things, and also you do not spend money to get the oxidizer. Okay, it comes free. So, that is the hallmark of air breathing propulsion, that we are not carrying the oxidizer and it comes free from the atmosphere. So, we only have to spend money for the fuel, only the fuel costs. Okay. So, how does what is the composition of air? We know that for every point we know that air is composed of 21% volumes of oxygen and approximately 79% nitrogen, and the rest are, there is also some amount of small amount of carbon dioxide and also inert gases, etc. So, for every, we can write that for every 4.76 moles of air, there is 1 mole of oxygen and there is 3.76 moles of nitrogen. Now, please note this number 3.76, it essentially is comes from dividing 0.79 by 0.21. Now, this we will use this number very often, because most likely, because as we, the topic of the title of this course is air breathing, essentially combustion and air breathing engines. So, we will only deal with hydrocarbon burning in air. So, we will frequently encounter this number of 3.76 moles of nitrogen. So, let us consider the overall combustion reaction of methane, in which this is methane and this is oxygen, and it produces 2 moles of water and 1 mole of CO2. Okay. So, first we define something like an equivalence ratio. Equivalence ratio is the fuel to oxidizer ratio, the actual fuel to oxidizer ratio divided by the stoichiometric fuel to oxidizer ratio, which you probably already know. Now, fuel lean, of course, if it is between 0 and 1, it is fuel lean, and if it is between 1 and infinity, it is fuel rich. Of course, you see that this fuel lean and fuel rich definitions are not very do not occupy the equal ranges in it do not occupy equal ranges. So, we can also define a normalized equivalence ratio phi capital, which is defined as phi divided by 1 plus phi, and this gives a more symmetric definition for fuel lean and fuel rich. Of course, you must remember that if it is this though we define phi from 0 to 1, this does not mean that combustion happens between phi from 0 to 1. It only happens within certain range of phi, and which will be later defined as flammability. Okay. So, now with this we need to review the concepts of classical thermodynamics. Now, let us go slowly over this. It might appear a little bit new, but this is important to introduce the classical thermodynamics in a slightly different manner, and this is mainly taken from this the concepts are basically taken from this book, Herbert B. Kallen, Thermodynamics and an Introduction to Thermostatics. So, what are the postulates? There are basically 4 postulates, and there can be several corollaries, which will not go into that. The postulate states that there exist particular states called equilibrium states, which you might be aware of. Equilibrium states in thermodynamics here, where basically all the motivation is to find out these equilibrium states and the characteristics of these equilibrium states. So, this says that there exist particular states called equilibrium states of simple compressible systems that macroscopically are characterized completely by the internal energy U, this is internal energy U, volume V, and the mole of the particle numbers or mole numbers N1, N2, Nk, that is if you have different species in your system like methane, oxygen, etc. So, the mole numbers of them of the chemical components. So, a state can be essentially characterized by the internal energy U, the volume V, and the particles number or the mole number. Okay. Then it states that there exists a function called entropy S, which is a function of these extensive parameters u, v and n. Now, you remember what are extensive parameters? Extensive parameters are those that depends on the size of the system, right. And if you say double the size of the system, the magnitude of the parameters also gets doubled, or if you triple the size of the system, the magnitude of the parameters also get tripled. So, S is a function of these extensive parameters, okay, of any composite system defined for all equilibrium states and having the following property. The values assumed by the extensive parameters in the absence of an internal constraints are those that maximize entropy for the composite isolated system. So, this says that these parameters, these extensive parameters u, v, n, I will act in such a manner that your entropy is maximized in these equilibrium states, okay. And the entropy of a composite system is additive. This is the third postulate, that entropy of a composite system is additive over the constituents of systems. Moreover, the entropy is a continuous differentiable and monotonically increasing function of internal energy. And this is the fourth, which is not really important now, it is called the third law of thermodynamics, that is the entropy of any system vanishes in the state for which d partial du ds v n equal to 0 at the 0, that is at the when temperature is equal to 0. These first three postulates are very important, and we will use them to essentially review chemical thermodynamics. So, if you see, if you go to this second postulates, it says that S is a function of u, v and Ni. U is the internal energy, V is the volume and Ni are the mole numbers, right. So, we can also write the internal energy is a function of S, V and Ni. If so, we can write du is equal to partial du ds dV over all species I is equal to 1 to n, say there are total n species, okay. So, this we can write. Now, we can define, using this we can define certain quantities, that is we can say T is equal to temperature, we define it as this way, partial du partial ds when V and Ni is constant. We can define P is equal to minus du dV when S and Ni are constant, and we can define another new quantity called chemical potential, which is defined as d partial du partial dNi when S and V are constant, okay. Now, we can show that these definitions that we have defined actually corresponds to our known definitions of temperature, pressure and chemical potential. Using this you can show that if you define it like this, this quantity T will emerge as that quantity which will determine whether thermal equilibrium is attained, okay. That this quantity T will determine when or in other words when this quantity say T in two different components of a system which are separated by a non-adiabatic wall, when these two quantities are equal there will be no heat flow. Similarly, when this in two composite in a system which is separated into two parts by a flexible wall which can move, in these two components if this pressure P are equal, then you will see that it can be shown that mechanical equilibrium is attained. Similarly, for chemical potential you will see that once again if you have a composite system which is divided into two parts, and if mu 1 and mu 2 are equal, that is the chemical potential of the one system is equal to the chemical potential of the other systems, and if these two systems are separated by a permeable wall, then you will see that the matter flow will stop when chemical potential, that is mu 1 equal to mu 2. So, temperature determines thermal equilibrium, pressure determines mechanical equilibrium, and mu chemical potential determines whether matter will flow from one system to other system when they are separated by a permeable wall. So, these then corresponds, it can be shown in this way. So, this then corresponds to our known definitions of temperature, pressure and chemical potential. We will not go into show how this can be obtained actually, but now we can even define new quantities, which is enthalpy, which is equal to U plus PV, we can define Helmholtz free energy, A is equal to U minus Ts, and we can define Gibbs free energy is equal to H minus Ts. Okay. Now, this quantity is, we will see that is very important for determining chemical equilibrium. Okay. Now, if you go to the third postulate or the let us go back, yes, if you go to the second postulate itself, you have seen that this part says that the values of the extensive parameters in absence of an internal constraints are those that maximize the entropy for the composite isolated systems. Okay. So, we can write, that means that the equilibrium criteria for a isolated system from the second postulate emerges as ds when UVN is equal to 0, and it can also be shown that the corresponding equilibrium criteria in terms of Gibbs free energy will be dg for Tpn is equal to 0. Okay. Now, when T and so what was the definition of so we defined that we defined G is equal to H minus Ts. So, what does this mean actually? Okay. So, this means that, so we can write, and of course, we have defined that G is equal to H minus Ts. So, we can define dg is equal to dH, if we differentiate, is equal to minus Tds minus SDT, and that is equal to du plus PdV, that is if we differentiate H itself, where H is equal to U plus PV. Okay. Now, let us go back to what we defined U as. We defined U as du, that is if you go to this thing, this is du is equal to Tds minus Pdv plus summation I is equal to 1 to n mu I dni, right. This is what we obtained, that is this is if you substitute these things here, if you substitute these things here, if you substitute this thing here, this is what you get. And now, if you substitute this thing into this, what you get is dg is equal to Tds minus Pdv plus summation I is equal to 1 to n mu I dni plus Pdv plus Vdp minus Tds minus SDT. So, you see that Pdv cancels, Tds cancels, and you are left with this and this. So, we define, we get dg is equal to vdp minus sdt plus summation I is equal to 1 to n mu I dni, right. So, now if we apply the equilibrium criteria, that is this onto this, at T and P is equal to constant, what we get is dg is equal to summation I is equal to 1 to n mu I dni is equal to 0. Now, please remember this is a very important thing. We will use this to arrive at more important concepts in chemical thermodynamics. Okay. Now, let us again go back to the concept that U itself is an extensive parameter. Okay. Now, as I said that it depends on the extensive means that it depends on the size of the system. So, if you double the size, it's the magnitude of the parameter also gets doubled. So, mathematically what this means is that if you define U is equal to lambda s, lambda v, lambda ni, then we can write lambda u is equal to s v ni. Okay. Now, mathematically this means that these are first order homogeneous quantities. Extensiveness essentially implies that first order homogeneous. Now, we can then invoke Euler's theorem and we can go into a first order equation of the form, if we write lambda xi y is equal to lambda xi, which can be any variable as such, and y is equal to lambda xi, just like we have written internal energy. If we can write it for a general variable y, dependent variable y, and the general dependent variable xi, we can, if we write this just like we have written for internal energy, and then whose differential is given by dy is equal to summation I gi dxi. Then by Euler's theorem, y is given by summation I gi xi. Okay. So, this is what it is. So, then it means that all the differentials that we have obtained for internal energy, we can remove and obtain the function or the parameter itself. Okay. So, this we can allow us to simply remove all the differentials in G etc. We can remove the differentials of internal energy and we can write it as internal energy as H u is equal to Ts. It was essentially du is equal to Tds minus Pdv plus summation I mu I dni. So, by these things, by this Euler's theorem, we can write u is equal to Ts minus Pv plus summation I mu I ni. Okay. And now, we can use this to substitute in the Gibbs free energy. Okay. So, which is essentially G is equal to, we know, is equal to H minus Ts is equal to u plus Pv minus Ts. So, we can substitute this here, and this implies G is equal to Ts minus Pv minus plus summation I is equal to mu I ni plus Pv minus Ts. So, this cancels, this cancels. So, this implies G is equal to summation I mu I, just one second. This implies G is equal to summation Ni. Okay. So, then this becomes the definition of G. Now, the reason why I have gone through all these things is that in many books you will find that this is defined in a little bit convoluted manner and this comes arbitrarily. Now, I myself could not understand these things and it took me some amount of time to understand how this is arrived from dg, how you can arrive at G is equal to summation mu I Ni. Now these are very important and very fundamental concepts which we need to be which needs to be clarified. Okay. Now, so we have obtained this, and let us erase these things. So, now, so we will go back, we will just have obtained two very important things, that is, for equilibrium we have obtained dg is equal to summation I mu I dni is equal to 0, and we have obtained the definition of G, okay, which is given by summation I mu I ni. But remember, the difference is that this is a differential, this is the actual G parameter itself, the quantity itself. Okay. So, now let us go and apply this to a real chemical reaction and see how we can, what property we can obtain for that for that chemical reaction. So, in general, you can say, suppose you are having a chemical reaction like H plus O2 going to OH plus O. Now, of course, you know that this is one chemical reaction which is very simple. So, this all the stoichiometric coefficient, this is 1, this is 1, this is 1, this is 1, right. Now, of course, there can be numerous kinds of chemical reactions. So, we need to have a general representation, and the general representation for this can be like something like I can write I can write a general reaction like y is equal to 1 to n nu I dash mi. Nu I dash is the stoichiometric coefficient for the reactant, mi is the name of the species, which goes to summation I is equal to 1 to n nu I dashed mi, okay, and this is the name of the product, and this is the stoichiometric coefficient of the product. Now, it goes to 1 to n in both sides. So, if you apply this to now this equation, n is equal to then is 4, because in the total reaction we have 4 species: hydrogen atom, oxygen, 1 hydroxyl radical and 1 oxygen, right. So, let us these things so that it is not confusing. All right. So, here if you see that our nu I dashed for H, if I write the name of the species and nu I dashed and nu I double dash, and this is say our mi, okay. So, for H we have nu I dash is equal to 1, nu I double dash is equal to 0, okay, because it does not appear on the products. So, we can say the stoichiometric coefficient of H in the product side is 0. For O2 we have 1, we have 0. For OH we have nu I dashed is equal to 0, and for this is 1, and for O we have this is equal to 0, this is 1. So, this I hope explains you the principle by which you are writing this generalized equation, okay. Now, this is just for a demonstration purpose, and but this is I mean the reason for introducing this kind of notation is that this is if you are suppose writing a going to read a code, a commercial code or a research code, and you are going to read the manual or going to read literature, you will find that there this the reactions are represented in this generalized manner and not really in the this manner. So, it is important to get familiar with the state of the art notations also, okay. So, that is why I have introducing this kind of notations. All right. So, now say this is our generalized reaction which we will use throughout this kind of generalized reaction notation, and now now by element conservation we can say that we can write essentially dni divided by nu I double dash by nu I dashed is equal to dnj divided by nu j double dash by nu j dashed, and that we can represent by a progress variable lambda, which is the reaction progress. So, for this d lambda amount of reaction progress, this amount of ni is can be produced or consumed depending on the sign, and this is proportional to their stoichiometric coefficients, rather the change in the stoichiometric coefficients between the product side and the reactant side. All right. So, we can write dni is equal to nu I double dash minus nu I dashed times d lambda, okay. So, we can now substitute this here. So, the condition of equilibrium becomes dg is equal to summation I nu I double dash minus nu I dash times mu I times d lambda. Now, d lambda does not depend on I, so that can go out. So, this is it. This is equal to 0 for equilibrium. Okay. Now, we will come back to this. Let us remember this and we will come back to this very soon. Now, let us consider a single ideal gas at constant temperature, okay, need not be in equilibrium. So, for that we can write dG is equal to VdP, and for the ith pure component of the ideal gas we can write d mu I is equal to V by Ni dPi. I will not derive how you do this, and this is left as a little small exercise to you. So, you can check how you can basically go from for a system not in equilibrium, how this can be arrived at. This is very simple, just you have to take the differentials. Okay. Now, for an ideal gas we know that P we can know that Pi V, whereas Pi is essentially the partial pressure of the gas, is equal to Ni times RT, right. So, V by Ni is equal to RT by Pi. So, substituting this here we get d mu I is equal to RT dPi, and now we can integrate on both sides from a given reference state from Pi 0. We will actually define this reference state to be Pi equal to 1, that is, which can be like 1 bar and Pi, then this gives mu I T minus mu I 0 T is equal to RT ln Pi by Pi 0. Pi 0 is equal to, we can say, always 1 bar, or and that is our this is equal to 1. Okay. So, the equation we have obtained is essentially mu I T actually is also a function of pressure, of course, as you see, because it depends on the reference pressure which is it has arrived. Okay. Yeah. So, this is a function of pressure also. Okay. Fine. Now, if we go back to our definition of equilibrium, we have already obtained dG is equal to d lambda summation I is equal to 1 to n mu I double dash minus mu I dash, that is the difference of the stoichiometric coefficients from the product side to the reactant side, mu I, this is equal to 0. Now, of course, d lambda is arbitrary, so we do not need it. So, this is the equation that we obtain. Now, what we can do is that we will basically substitute this thing here. Okay. So, if we do that, we obtain summation I is equal to 1 to n we can take this part on the right hand side this is equal to because of the properties of the logarithm okay, and this quantity is called the equilibrium constant Kp in terms of pressure, equilibrium constant in terms of pressure, which is only a function of temperature. Why is it only a function of temperature? Because what you have on this side is essentially, if you bring this down here, so if you take this here in the denominator, so this is a function of temperature alone, this is a function of temperature alone, so this is ln Kp can be only be a function of temperature alone. Okay. So, you must always remember that though it is Kp, it is only a function of temperature. Okay. So, and of course, you see what it is, essentially it is a product of the different partial pressures raised to their stoichiometric factors, stoichiometric proportionality, stoichiometric constants for the given reaction. Okay. So, that is what Kp is, and this is a very important tool to understand, to estimate why we have got this. This is a very important quantity which can be, you can find in different kind of tables for a given reaction or for other things. Using the Kp, we can find out what is the composition of chemical equilibrium. That is, what is the combustion, what is, if you are interested in understanding what is the composition of the combustion products, that is given by Kp. So, that is why it is a very, very important constant, but remember always that it is a function of temperature alone. Okay. So, what we have obtained is that we have obtained this thermodynamic function, we have obtained this criteria for chemical equilibrium mu I, d and I. Here the overbar essentially represents when it is in terms of moles, which we have also used. So, we have obtained the general expression for chemical reaction, and by applying element conservation, we have obtained the criteria for chemical equilibrium to be this, and we have obtained derived the Y chemical potential should be in this manner, whereas P0 is 1, and then we have obtained the equilibrium constant Kp, which is given by this. So, this is what we have obtained, and the final expression for Kp as given here is this one. Okay. So, now as I said that you can see it is written here that the Kp can be at a given temperature can be tabulated for a given reaction. Okay. Or alternatively, one can also find define another equilibrium constant, because you can relate partial pressure and concentrations, and with that you can define Kc, and Kp and Kc are also related in the following manner. Okay. And also we will see later that this can be utilized for estimating a rate constant of a backward reaction if a forward reaction is known. So, this has got multiple use. Now, how do you obtain Kp? You can obtain, of course, there are numerous kinds of reactions that are possible. So, it is very difficult to write down the Kp for each of them. So, the best idea is to basically estimate it somehow. So, we can write that, we can state that the Kp we can define a Kp for the formation reaction of each species. That is, we can, if we are concerned with a species Mi, which can be say like a CO2, we can write the formation of CO2 like formation of C plus O2 goes to CO2, and you can basically define the Kp of that reaction itself, that is the reaction of formation of the Kpi, and the purpose is basically to obtain is to basically have a relationship of Kpi 0 and this chemical potential at the standard state, and by substitution you can obtain the Kp in this manner. Okay. So, often you will find that instead of the Kp of the reactions, the Kp of the formation of the species is given, and then using these kinds of the Kp 0 for the individual species, you can estimate the Kp of a reaction involving those species. All right. So, this is how we can estimate the equilibrium constant. Now, why is it useful? What do you do with the Kp? As I said, the Kp is used for basically identifying or finding out the composition for the products which are in chemical equilibrium. Now, for hydrocarbon oxidation, that is if you say methane oxidation CH4 plus oxygen, that goes to, if this two methane burns in oxygen as well as in some amount of nitrogen, and if we assume that the nitrogen is not participating in the reaction. Okay. So, the main products that you will get is CO2, water, and if it is lean, then you can have some leftover oxygen, and if it is rich, you do not have any leftover fuels, but you have basically CO, carbon monoxide, and hydrogen as which are also some kind of fuels essentially. So, you can use this to basically find out the equilibrium, the composition. Now, for fuel lean mixtures, there is no problem actually. For fuel lean mixtures, that is, suppose it is propane burning in air, this is air, right. So, for burning 1 mole of propane, you need 5 moles of air, okay, and phi is essentially the equivalence ratio in front, which is something between 0 and 1, and you will see that there will be, for phi moles of propane, there will be 3 phi moles of CO2, there will be 4 phi moles of water, and you will have some leftover oxygen in this form, and then this is constant because it does not participate in the reaction. So, this is predetermined. This is, you do not need equilibrium constants to find out the composition of CO2, water, and oxygen, because these are uniquely defined through element conservation. That is, just by looking at the reaction and by looking at how the 3 moles of C, the 3 molecules of C in the propane and 3 atoms of C and 8 atoms of H in propane, how they are how it is the formula for propane and the formula for oxygen and nitrogen, etc. You can find out how many what will be the proportionality constants for, what will be the stoichiometric constants for CO2, what will be the stoichiometric constants for water and for oxygen and nitrogen, so on and so forth. So, this is uniquely defined. The problem arises when you have rich mixtures, or in some cases when you actually include more species. Then you cannot basically, if you include more species in your equilibrium in your products, of course there are, these are not the only species that is produced, that is at equilibrium in a combustion reaction. You can have some hydroxyl, you can have some CO, some trace amount of CO, etc., and many other molecules that will be formed. So, if you include more species, you will actually cannot determine the equilibrium composition through just this elemental balance, and this problem is clearly identified here when you have fuel rich mixture, that is when you burn propane in oxygen, and when phi is greater than 1, then of course you produce CO2, but you also produce CO, you also produce water, you also produce hydrogen, and you also produce nitrogen. So, how do you know that how many moles will go to CO and how many moles, what will be the what will be B and what will be A, which are the stoichiometric coefficients, okay, and what will be C and what will be D. Now, by applying element conservation, we can basically by applying element conservation between C, H and O, okay, which are the only elements which are participating in the reaction through different molecules, we can have three equations, but as you can see we have 4 unknowns. So, where will the other unknown come from? Okay. So, for that we need an initial reaction, that is a water gas shift reaction, and for that we need to know the Kp of that. Okay. So, using that, the Kp of that will be defined by this, because if you immediately apply the derivation of Kp that we have obtained in terms of the partial pressure raised to the stoichiometric coefficients for this water gas shift reaction, you will immediately find that Kp is this form, and then you can find BCB, you can find this will be a proportional to B times C times divided by A and D, and if you can get this from the table, you can get this from this value from the table, and we can find the additional equation that was missing to derive the 4 unknowns. So, like this, using Kp you can find out the equilibrium composition, the product, the equilibrium composition of the products of combustion reactions. Alright. So, this class ends here. Next we will see how we can apply energy conservation to basically obtain the temperature of the adiabatic flame temperature for a combustion reaction. Thank you.